This video is going to be on a concept known as Le Chatelier's principle. It is French. And before we go into that, I just wanted to kind of really show what it means, because you could honestly do this without understanding what it means, and we always want to understand everything all the way through. So let's start with just establishing equilibrium, right? We're reminded that you could have any kind of situation, like in this reaction, A going to B, where we could have some of B, some of A. We could have all of B to start with, or we could have all of A to start with. And essentially, eventually, that reversible reaction will establish equilibrium, right? So in this case, we started with all of A, and those particles start to transfer over. And then we start to see B going to A and some of A going to B, right? We're getting closer to equilibrium. And then we see, again, they switch back and forth again, until eventually we get to a point where the rate forward is equal to the rate backward, which we just established. We have 7 going one way, 7 going the other. But generally speaking, it could be more complicated, but the rate of A going to B is equal to the rate of B going to A. From here on out, we said that the changes would keep occurring. A would switch to B, B would switch to A, but it wouldn't visibly appear as anything occurring because no changes are occurring. The total number of A and the total number of B will remain constant, even though they're swapping like that. And if we looked at the graphs of these, this showed a flat line, right? This showed that A and B would remain constant. They would just be going across like this pretty much. They'd be constant at equilibrium. That's how we knew they were at equilibrium. Okay, the purpose of this video, and also remember that we had different numbers of each one, right? 13 and 27. The purpose of this video is to look at Le Chatelier's principle, which talks about making predictions about what changes will occur to the equilibrium when a stress is applied to it. Now, a stress could be changing the added amount, removing some things to lower the concentration, changing the pressure, things like that. Changing the temperature. Those different things will affect. So we are going to be able to, at the end of this, know exactly what changes will occur. But let's take a look at exactly what we're talking about, though. Here is our change that will occur. So remember, at this point, we've established equilibrium. These changes occur to an equilibrium. So you're only going to do it once you've actually already established equilibrium. And instead of having 13 particles at the end here, I'm now going to have 24. So I'm going to add those babies in. We're going to be starting with that. Now, at this point, we've made a change. So we are no longer at equilibrium, and the system is going to have to adjust itself to try to get there. So we're going to see equilibrium reestablish itself, but what we want to see when that happens is what occurred with these particles. We're starting with 24 of A and 27 of B. And which way will they shift? Will B have more in the end, or will A have more in the end? So let's see. So equilibrium starts to be established. We're not yet there, right? We have unequal numbers shifting from both sides. Still shifting. Now we've reestablished equilibrium, but let's take a look at our count at the end. We have 17 in A and 34 in B. So what we're saying then is that the equilibrium shifted to the opposite side that we added to. We added particles to A, and that caused the equilibrium, in order to make up for the stress of it, to shift particles to B when it reestablished equilibrium. So we added to the left, equilibrium shifted to the right, or more correctly, we tend to say equilibrium shifted toward the products. As a result, we have more products. So this is a useful situation if we had a reversible reaction that we wanted to try to get a desired outcome. We want to try to drive it to make more of one of the either reactants or products. Maybe it's some process that we need either reactants or products for in industry or something like that. But yeah, so that's the general of what we just looked at, is that if an external stress is applied to a system at equilibrium, the system adjusts in such a way that the stress is partially offset as the system reaches a new equilibrium position, right? So we have equilibrium, apply a stress, system shifts to achieve equilibrium again, and the change that occurred is what we're focusing on. So if we change the concentration, for example, if we add NH3, so this is going to be a little bit confusing, but remember that these are actually all sitting in the same reaction vessel. Imagine like the same cauldron, the same beaker, the same whatever it's the same test tube, whatever it's occurring in essentially. These are all actually in the same test tube, but in order to help us visualize, we're going to imagine that we're adding things to one side. So if we add NH3, you are considering it to be added to the side where it already exists, right? So technically you're adding it literally to a test tube or whatever you've got all these in, or in case of gases, like a sealed container. But for our purposes, to make it easier, we imagine that we're adding it just to the product side. So if you're adding NH3, NH3 is a product, so that means we're adding to the product side. Whenever you add something to the product side, equilibrium will shift to the reactant side in order to offset the stress. And then so we kind of see that here, where you see the flat lines. I love this visual. We originally are at equilibrium because they're flat lines, right? H2, NH3, N2, we're all at equilibrium. Then there was a change that happened where we see a spike in NH3. Somebody added NH3 in. As a result of that, we then see NH3 will go back down as equilibrium is reestablished, but H2 went up and N2 went up. So I literally just imagine it as like you add it to the one side and it's squishing over to the other side, making more of the other side. It's like someone's literally pushing it to that side, like forcing these through the arrows to produce more of these. This is what I sort of picture it as. So literally if we're adding A and B reactants, it would be like pushing it over and creating more of C and D. That's my sort of visual that I picture. Now the opposite can happen too. If we remove particles from one side, let's say we're removing them from the left, I imagine there's like a rope or something connecting all these, and as I remove from the left, I'm literally pulling it to the left, causing other things to also shift that same direction. So here's sort of our summary of what happens. So if we add to C and D, in this case, we're increasing concentration of the products, the equilibrium will shift to the reactants. Shifts to the left, we say. And if we were to remove C and D, the equilibrium will then shift toward that same side. So that's sort of our summary. Whatever side you make more concentrated or add to, equilibrium shifts to the opposite side. And whatever side you remove from or decrease the concentration of, equilibrium will shift to the same side. So adding goes to opposite, removing goes to the same side. I picture like that pushing and pulling. So if we were to add A and B, the reactants, then we would get essentially a shift to the right. And if we were to if we were to remove from A and B, that equilibrium would then shift in that direction. So that's the change that we would see. So that's just for concentration. Now we're going to look at a change in volume and pressure. So just of course we can kind of visualize if we are decreasing the volume of a container, we would expect more pressure in gases, right? More collisions to the sides. And if we're increasing the volume of a container, we would expect less pressure. So that's how these are related. When we do that, it's a little bit different of what occurs. So let's say we're increasing the pressure. This is an example system. We've got Cl2, CO, and CO, Cl2. So two separate chemicals that react to make one chemical overall. Up in this visual, you actually see a couple of those, but you see like kind of double all of these is what's occurring. You got two Cl2s, a couple of COs, and a couple of Cl2s. Okay, but what happens is if you increase pressure on the system, the equilibrium will shift to the side with the fewest moles. So remember, these are all actually in the same container. So we're putting pressure on the entire system, and equilibrium then shifts to the side with the fewest moles. I think an easier way to think of it is like you're literally squishing them together to make fewer things. Like if you're squishing chemicals together in this situation, they're trying to be as few particles as possible then. You're literally kind of forcing them together, squishing them. So in a high pressure situation, see the 1 atm, actually this visual is not that great, but imagine, so essentially this left side actually has more pressure on it. So we're forcing the equilibrium to shift toward products. So this is actually all products here. This is COCl2 that's contained in here. But if we relieve the pressure, and see how the plunger kind of comes up, if we relieve the pressure, then we actually have more moles because you're actually making things less compressed, and they're more comfortable kind of separating into smaller pieces, into their smaller pieces that are on the left side in this case. Also, if we go to count, we have 1, 2 moles on this side, just 2 different chemicals pretty much total. And then on the right side, we have 1 mole in our balanced equation. So you kind of want to, you want to count the numbers, add up the coefficients on one side, compare them to the coefficients on the other side. And then whichever has the smallest number, an increase in pressure will shift to that side. A decrease in pressure will shift to the side with the greater number of particles. You're kind of allowing them to be separate and take up space, really spread out. So increase in volume is synonymous, right, with a decrease in pressure. So then we go again with the side with the most moles of gas, and then a decrease in volume is synonymous with an increase in pressure, typically. So we go to the side with the fewest moles. So squishing the particles together pretty much. Okay. This is our pretty much last item on here. So what we want to be able to visualize, and doing a web assignment or doing these problems, you're going to have to write this in when it occurs probably. If you have an exothermic reaction, right, even a reversible reaction, one way that's symbolized is to put heat as in the products, which makes sense if you think about it because exothermic is actually releasing heat. So we think of heat as being sort of produced. It's a product overall of the reaction. So we're literally just adding in, and once we put that word heat in, then exothermic is going to go on the right side. In endothermic, it's like we're putting heat into the system, right? Heat is entering, so it's going to be on the left side. An exothermic heat is exiting, so it's going to be on the right side. Another good way to look at it. But the nice thing is, once you've added that word heat in there, then you can just treat it like a reactant or product, and the rules don't really change. So let's take a look. So for example, let's say we increase the temperature. Increasing the temperature is like adding heat, right? So for an exothermic reaction, that's like adding products. So that will shift the equilibrium to the left. Also, don't forget our equilibrium constant K will change. It'll decrease. That's the only thing that will change the equilibrium constant K is temperature. But okay, so if we add heat to the endothermic reaction, that's like adding a reactant. Equilibrium shifts to the right. Also, in terms of K decreasing, K increasing. Let's see. So that makes sense. If we're shifting equilibrium to the left, then that means we've got more reactants and fewer products. So yeah, K will go down, right? Because it's products over reactants. We're creating a larger numerator. I mean, sorry, a larger denominator because it's products over reactants. And in the opposite situation, we are shifting. If we shift to the right, that means we're creating more products, right? A higher numerator and fewer reactants, a lower denominator. So that makes K increase because K is products over reactants. Okay, but a decrease in temperature, right? That's effectively the same thing as removing heat. So we're taking heat away from the right side, which means equilibrium will shift to the right, shift to the same side as the removal. And then K, you can figure out why that makes sense again as well. And then if we're decreasing temperature, we're removing heat, that will shift this one to the left side because we're removing reactants. So it's kind of not even that much more to remember. It's kind of the same exact thing. Adding a catalyst does not change the constant. It does not shift the position of an equilibrium system. The system will reach equilibrium sooner. So here's kind of a visual of that. Remember, so we know that a catalyst will lower the activation energy, but it'll actually lower the activation energy in both directions. So it won't actually change anything overall, except you'll reach equilibrium faster. But yeah, it's kind of making that hump lower. But either if we're going from AB to CD or from CD to AB, it's lowering both. So it lowers the activation energy EA for both forward and reverse reactions, and doesn't change the equilibrium constant or shift equilibrium. Okay, so here's our overall summary. A shift in equilibrium. If we change the concentration, it will shift the equilibrium, and it will not change the equilibrium constant though. Ratio of products to reactants will remain the same. Pressure will shift equilibrium, will not change the constant. Changing volume will shift the equilibrium, will not change the constant. Temperature is the only thing that will change the equilibrium constant. Right, so that's the only one. And then the catalyst will not shift the equilibrium, and it won't change the constant. So that would be like a pretty good test question on there. Okay, so that's it for this video.